All right. So what we've done in chapter 3 and learning to solve systems of equations is kind of leading us into this next chapter where we start looking at we start using solving systems of equations as in order to answer other kinds of questions. So what we're going to do here in section 4.1 is we're going to start with this. We're going to start talking about, for the moment, plotting some points in three-dimensional space. Okay, so of course, hopefully you've had a little experience with this, right? We have our x-axis, we have our y-axis, and our z-axis, and I'm just showing the positive of each of these, and of course, if I want to plot a point in three-dimensional space, I just want to plot the point 1, 2, 3, right? X coordinate, y coordinate, z coordinate. I go out the x direction 2, over the y direction, sorry, let me back up. Out the x direction 1, let's do that. Over the y direction 2 and up 3, and we get kind of a point that lives about right there, and there it is, right? Now, just so you don't have to suffer from my artistic ability, we can throw this into Desmos. Desmos has a great way to do this. If you bring up Desmos and you click on 3D graphics, it kicks you into 3D graphics mode, shows you your XYZ axis. Now just so you know, XYZ, they're not labeled, but the way you can remember it is red, green, blue. So red is X, green is Y, and blue is Z. There's what it looks like. Positive X, positive Y, and Z. Okay, red, green, blue. But the point, 1, 2, 3, there it is, right? And we can kind of move this around and you can see it, right? That's kind of nice. So we can plot points in three-dimensional space. Now, here's what we want to do. We're going to, we can view this as a point, but this could also be viewed as a vector quantity. Okay, so there are some physical quantities that we measure with vectors. All right, so velocity is an example of that. When we talk about using a vector quantity, something being a vector quantity, what that means is not only do we care about how what its magnitude is, how big it is, how much wind there is, how hard the wind is blowing, but we care about the direction the wind is blowing. So a vector quantity is a quantity that has both specific direction and specific magnitude. If you need to get a little more entertaining view of that definition, go watch the first movie with the Minions, whatever that was called. Anyway, there's the bad guy there is called Vector, right? He commits crimes with direction and magnitude. It's the highlight of the movie. Check it out. Anyway, so what we do is this could be represented as a vector, which is quite simply just an arrow, and we put that arrow. The arrow could be anywhere. It's just got to be a certain length long, and it's got to be pointing in a certain direction. Okay, so you know it's going to be the same arrow wherever you put it, but we put these arrows in what we call standard position so that they all start at the origin. Okay, so to graph a vector in in GeoGebra, you use the vector command, and then you put the point 1, 2, 3, and you see now what has happened is it's drawn that arrow to my point. It starts at the origin and it ends at that point. Okay, that's just in standard position. What this arrow could be drawn here. It could start here, and as long as it went in the same direction and had the same length, then that's still a vector quantity. Okay, but like I say, we don't worry about that. We just say, okay, let's assume that's our vector. Okay, so now we start thinking about these vectors and what we can do with them. First thing we do is we could add vectors. Okay, so suppose I have the vector, let's just call it, here we go. Oh, yeah, we'll just do it this way. Let's call it 4 minus 3 minus 1. You got to put parentheses around that. There we go. Okay. 4 minus 3 minus 1. Bam. There it is. And so see, now it's pointing down there, right? It's pointing in this direction. And it is, it looks like it's a little longer. It has a larger magnitude of that than that, okay? But those are two vector quantities, okay? So those are two vectors. Well, it turns out we are interested in things like adding them. What happens when you add these? So u plus v, not uy, u plus v. What you get, let's see. This is our sum. Let's change our color here. So there's the sum vector. This is vector 1, this is vector 2. Right there. Okay, so you've got your two vectors and you add them, and you can see that here, but let's talk about how that works. To make this simpler for me to demonstrate on paper, we're just going to work in 2 dimensions. Okay, we're just going to work in 2 dimensions, not a big problem. So make our lives a little easier. So let's just deal with the vector 2, 1. So there it is right there. And then let's deal with the vector 1, 4. And there's the vector 1, 4. Okay, so if I want to add them, all I do is I add the components together, the x components and the y components, right? So we call this vector u, we call this vector v. So u plus v is simply x coordinate plus x coordinate, so 3, 1 plus 2, and then 4 plus 1. 3, 5. So we should get the vector 3, 5. Okay, there it is. Okay, so now there's a couple ways to visualize this, and I think it's helpful to think about, to realize this. If I were to take u and put another copy of it, but start here, right? Go in the same direction and the same length. So that is just a copy of u. Look at that. I get, basically what I've done is I've started off with v. Do this, come on now. Started off with v, and then I've tacked on u, and look where I end up with the sum, right? Or if I do it the other way, if I go u first and then start at the end of u and put in a copy of the v vector going in the same direction and the same length, all of them meet right there at the end of that green vector, which is the 3, 5 vector. Okay, so we get what's called a parallelogram rule, right? That is, when you add two vectors, the result is basically the diagonal of the parallelogram formed by the vectors. But for me, I always kind of like visualizing, taking u first and then tacking on a copy of v, and then wherever I end up, that is the sum. Okay, so again, that's in 2 dimensions, but it works the same in 3 dimensions, but it's much harder to draw. Now, u minus v, same thing. You just subtract components. Of course, the order matters, right? You're going to go the u components minus the v components. 2 minus 1 is 1, and 1 minus 4 is minus 3. You don't have quite this nice trapezoid rule with subtraction. But as far as completing it, it's no big deal. The other thing we can do with vectors is we can multiply them by a scalar. So if I take u and multiply it by 3, that's going to happen. That's going to result in something that I think is fairly intuitive. You just multiply the components of u by 3. So 3 times 2 and 3 times 1. Okay. And so what you get when you do scalar multiplication, graphically speaking, is you get the u vector, okay, but it's going to be in the same direction, but it's just going to be stretched 3 times longer. So it's going to be, there's one of them, there's about 2 of them, and there's about 3 of them. So this would be the vector 3u. So it's stretched 3 times as long, but notice it goes in the same direction. I could multiply by a negative, and if I multiplied by a negative, it would go in the exact opposite direction. If I multiply by 1, this would be the negative u. It's the same length, but in the opposite direction, 180 degrees away from the original u. If I multiply by negative 2, it's twice that, but in that direction. Okay. So again, 2 dimensions, I can represent it fairly easily, but you just have to imagine working that in 3 dimensions, or you could throw it into GeoGebra and let that work. Now, so what we've got is we've got addition and subtraction by default, right? We'll just refer to addition, and we've got scalar multiplication that we can do to vectors. And what happens if you add 2 vectors? You get another vector in 2-dimensional space or in 3-dimensional space. If you multiply, if you do scalar multiplication, you get another vector. Okay. So and then we have all the standard kind of arithmetic properties, right? We have commutativity, right? If I take the vector u and add to the vector v, that's the same as if I go v plus u, right? I have associativity when it comes to adding vectors. I have a 0 vector. I have the distributive property. All of those things come into play when we're dealing with vectors. Okay. Now, so it doesn't matter if it's two dimensions or 3 dimensions. That's what you've got. Now I should mention this. When we talk about vectors, we typically refer to them using bold. Okay. So the vector v was 1, 4. Okay. Vector v is 1, 4. Sometimes if we can't use bold, like I can't really write in bold, sometimes we'll just write with a little arrow above it. 1, 4. Okay. So that's kind of the approach we'll take. Sometimes we'll put it right as a column like that. But in general, you'll notice, and I've already done this, if we're talking about vectors, if the context of the discussion is vectors, I don't even write the arrow because we're just talking about vectors. Okay, so we have this interesting world of mathematical objects known as vectors. We can represent them graphically, and now we're going to study them and see what they have to tell us, what we can learn from them.